thermosetting plastic and thermosetting plastics, we shall be in position to look at what we call the natural rubber. So we have natural rubber and artificial rubber. If you don't want to call it artificial rubber, you can say synthetic rubber. Now, when you say natural rubber, this is obtained. This is the history. It is not chemistry, but this history is telling us that we can really get this one from where? From these all those other things. So this is obtained from latex, which is a colloidal solution in white fluid found on the bark of tropical trees. So there are those trees that when you cut the bark like this natural rubber will be in position like to flow out, and it is white, of course, white fluid. So it flows from the bark when the tree is cut down, because it is then coagulated by addition of ethanoic acid. So this chemistry, when you look at it critically, we talk about what we call the carboxylic acids or alkanoic acids. So with this knowledge, you'll be in position to say that when you talk about ethanoic acid, I'll be in position to at least write something like this and say this is the what? The ethanoic acid. So that means if I have a container, like this, then I put now this is what we call the natural what? Natural rubber. I put it here. Okay, I've collected it from this cut back of tropical trees, and I want to coagulate it. I will be in position to add what? Ethanoic acid. So this chemistry is very, very important. Then at the end of the day, this rubber is the polymer, of course, and it is made by what we call addition polymerization. It's not additional, it is addition polymerization of, now here come a very good chemistry for us, of 2-methyl butyl 1,3-diene. Now, when we are talking about alkenes, alkynes, we are talking about naming these organic compounds, and we follow what we call the IUPAC name. It is IUPAC names. But also we say that when we are following that international union of pure and applied chemistry, we shall be in position to at least follow some rules. And those rules, when you go back and check critically, you'll be in position to get them. That's why when I'm ahead here, I will start naming them, and you will not be in position to get confused. So here, when you look at this is the straight chains and this is the branch chains. So a student of chemistry will start numbering from here and say this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. On the what? On the long chains. You want to come up with 2-methyl butyl 1,3-diene, how the thing came about. Then we have seen this is the branching. So the branching is on the carbon 2. Then now this branching is what we call the methyl group. So after seeing this, you'll be in position to say, where am I going to start from? I should start from this carbon atom, this positional. So we say 2-methyl, I'm meaning these 2-methyl, the carbon 2. This carbon, the position is there indicated. So 2-methyl. Then after that, I will say, let me go back to the long chain and I count 1, 2, 3, 4. I have 4 carbon atoms. That's what brought about but. Now, let's look at what we call the functional group. This in is the functional group for alkenes. Is a functional group for alkenes. Now, let's check the functional groups. This double bond, you see it here and you see it here. So that means I have 1 here and I have 2 here. So that's whereby we came up with here, this A you're seeing, butyl. Now again, we are counting these carbon atoms, and we see the position of these double bonds on these carbon atoms on the long chain. So we shall be in position to say this is carbon 1 and this one is on it. We are not placing it in this one ahead. We are placing in this one immediate. So that's why we say 1. We are meaning these carbon atoms and is attached to this double bond. Then we continue and say this one here, we don't put it for this. We put it to these carbon atoms to the left. This carbon atom to the left. So we'll be in position to say it here. I have 3, But then also this double bond, there are two. So if there are two of them, we say di. And then this one here, the functional group is in. That's why we came up with something like this. So 2-methyl buta-1,3-diene. Be in position to tell another student when you are discussing that part of very organic chemistry. Now let's look at the double bonds at the ends open. Now we're in the process of what we call addition polymerization. So here what happened is that this compound, after us getting it, it is called 2-methyl buta-1,3-diene, and we add the catalyst. There is also need for temperature here, which is not specified. When you go ahead with your chemistry, you'll be in position to get it. We shall be in position to form this polymer, and this polymer is what we call the natural rubber. So natural rubber is simply formed from these molecules 2-methyl buta-1,3-diene when there are very many in presence of these conditions, and we shall be in position to get ploy. Now this one is just you add the word ploy and you bring this thing and put it there. So here I will have ploy 2-methyl buta-1,3-diene. Now take note here. This is where students are failing. We have seen the double bond here and we have seen the double bond here. So this one here is telling us the double bonds opens at the ends. So those two ends, this one open up, this one open up. Now the reason is to allow what we call elongations that brings about that formation of the polymers. And then after that, there's what we call polymerization to form what we call natural rubber. So here, this natural rubber is being formed. After this one open up, this one open up, you will see the double bond will shift now and come here. Now, this one is simply for this process to continue and allow what we call the elongations. And at the end of the day, this N, you will see that N will represent the number of monomers in this polymer. It's just the number of monomers. How repeated are these in that very molecules? So, and we are saying the natural rubber can be used, of course, to make what we call the car tires. We have all seen tires of those cars. They are made of what we call the natural rubber. And we are saying the crude form of rubber is not elastic. So that means if it is not pure yet, or you did not like manufacture, you did not modernize it, that means it is not what? It is not elastic and it is not strong. So therefore, when you see the car tires, it means there was a process done somewhere to that specific natural rubber, and it is made stronger by heating up. This is the process we're talking about, heating it up with sulfur. What do we know about sulfur? Sulfur is an element among the first 20 elements, is number 16. But also it is very, very, very important when it comes to this process. So sulfur in the process called volcanization. So volcanization is simply the process of heating sulfur with the what? Natural rubber to form what we call a very strong and elastic natural rubber. This process form what we call cross linkages between carbon atoms and sulfur atoms. Now, if these are the carbon atoms, we have these are the carbon atoms. Okay, let's say in this natural rubber. And we're saying this one here, they are not elastic, it is not strong. So for us to make it strong, we shall be in position to at least hit this one with what? Sulfur. Sulfur atoms. So at the end of the day, what is going to be formed is what we call the cross linkages between the atoms of sulfur and the atom of carbon. Now, why is it important for us to at least volcanize this natural rubber? One is for us to get a greater tensile strength, and we shall be in position also to get this higher durability of what? Of the natural rubber. Therefore, when it is treated well with this sulfur through the process of volcanization, we shall be in position to at least get sulfur which is elastic and inert to many chemical reactions except burning. We're still giving the example of the car tires. That one is very strong. When you try to maybe put in what you call sodium hydroxide, maybe an acid, you just see it is very strong. But now when you set fire, then the thing will start burning. So that's when you are saying it is inert. It is inert. When you say something is not inert, I mean something is inert, we are saying it is not reactive. So unless when you're now burning this natural rubber. Now let's look at what we call synthetic rubber. For this synthetic rubber, it can be produced from what we call new purine. Now it is chemical called fluid 2-chlorobuta-1,3-diene. But now this is what we call a synthetic rubber. So when I say synthetics, that means it has been produced to other form of modernization in the process. And here we said this 2-chlorobuta-1,3-diene. Now I will not explain naming this because I explain how we can name this one, so you'll be in position to know how this one come about. So you add the catalyst, also there's need for temperature. We shall be in position to get fluid 2-chlorobuta-1,3-diene. Now, very important notes here. Sometimes we are not just to read, but at the same time, we need to understand and also apply the knowledge when we're given the exams. So there are some questions that I'm going to summarize here about this specific part. So here we shall be in position to say it. Part A, distinguish between addition, polymerization, and condensation, polymerization. Okay, I'm writing it in short, so this full stop. Part B explains the difference between, now I'm coming for plastics, between thermosetting and thermosorpting plastics. Okay, C, someone be in position to say, describe how a natural rubber can be made elastic and durable. Okay, part D shall be in position to generate another question here and say it. Write an equation. Write an equation for the polymerization of synthetic rubber from I can say it from 2-chlorobuta 1,3-diene. So these are just some of the questions that you will find in this very part. Thank you.